Thanks for everyone for coming. And so in this talk, I'd like to present our work in formally verifying asynchronous dataflow compilers. And this is on behalf of my awesome collaborators, E and Milijana from the University of Maryland. So in a few sentences, our work is about designing and building a verified compiler in Ling, targeting these novel architectures based on spatial dataflow, which is a historically difficult target to correctly compile general-purpose program into. That is programmed with irregular control flow and memory access patterns. And in our verification, we also try to use modular proof techniques, and we also leverage a front-end capability type system to guarantee the race freedom of the compiled dataflow circuit. So what is the motivation behind all this? This might be a bit of a cliche, but computing systems today are increasingly heterogeneous. So on one of the spectrum, you have CPUs, which are very programmable and flexible, and GPUs, which are great for massively parallel workloads like graphics and machine learning. But they waste a lot of energy in moving data around and are usually power hungry. On the other hand, domain-specific accelerators, or ASICs, are fast and energy efficient. However, they're wired to perform a fixed set of tasks, like for multiplying matrices, and the application domain is relatively fixed, like for writing ML kernels. So it's a natural question to ask whether we can find a balance in the middle to allow general-purpose programmability, like CPUs, while achieving energy efficiency and performance close to ASICs. So our work targets two lines of work in architecture that are pursuing this goal of enabling hardware acceleration for general-purpose programs. One such area is reconfigurable dataflow architectures, or RDAs, in which you have an array of processing elements, or PEs, in the hardware, and you can configure each PE to function as a high-level operator for arithmetic or accessing some shared memory. So these are similar to FPGAs, but the operations are like at the word level instead of logic gates. So one of the benefits of RDAs is that you can place these operations close to each other and spend most of the energy in compute instead of moving data around. And as demonstrated in prior work, Riptide, such locality can enable sometimes 100 times better energy efficiency on certain applications compared to off-the-shelf low-power CPUs. In a different line of work, people have been working on compiling high-level programs like in C to hardware designs, or in other words, doing high-level synthesis. While traditional HLS approaches try to find a static execution schedule for the source program and then encode that in the hardware as a state machine, it has been realized in recent work if we allow components of the program to be data-driven rather than following a static global schedule, we can achieve much better performance on irregular control flow. And this approach has been realized in HLS frameworks such as Dynamically. So despite coming from slightly different communities, these two approaches share a key compilation challenge. And that is how to bridge this gap between the more general-purpose workloads with irregular control flow and memory access patterns, and the actual hardware with abundant parallelism that we want to utilize. And a promising solution found in this prior work is the abstraction of asynchronous dataflow. So this representation has two important benefits. First is asynchrony. So in an asynchronous dataflow circuit, each operator or gate can execute as soon as input data is available without following a static global schedule, which can drastically improve the performance in programs with irregular control flow. The second is that by representing the program in this pure dataflow form, the hardware can be configured to maximize dataflow locality and achieve much better energy efficiency. Therefore, in the compiler pipeline, we can compile the source program into a dataflow circuit, which I'm referring to as the dataflow compilation here. Then the dataflow circuit can be much more easily mapped to an RDA for execution or further lowered to hardware designs for HLS. However, the benefits of asynchronous dataflow becomes challenges for correct and efficient dataflow compilation. So the semantics of this dataflow circuit can be thought of as a large collection of concurrent processes, and they would pass messages through these channels denoted by edges in this graph, along with potential concurrent accesses to a shared memory. So an incorrect compiler might introduce annoying concurrency issues like deadlocks and data races that are not possible in the original sequential program. But at the same time, the compiler has to soundly extract parallelism in the original program as much as possible, because if we overly synchronize the dataflow circuit, we would not be able to utilize the parallelism in the hardware. Larger applications in this domain may scale to hundreds of asynchronous and parallel dataflow operators. So trying to debug a data race or deadlock caused by the dataflow compiler would be a nightmare. So in other words, the central goal here is that we want memory consistency, but without sacrificing the performance and parallelism. In this work, we hope to use formal verification to prove the absence of these issues ahead of deployment. In particular, we design and formalize a dataflow IR and compiler called Wavelet, built using the Lin theorem prover. And we prove that the compiler produces an equivalent dataflow circuit along with good properties such as deadlock freedom, data race freedom. And importantly, our compiler and proofs are also structured in a way that enables an important optimization of dataflow pipelining, which supports more parallelism in the dataflow circuit. So let's see how Wavelet works at a high level. The source IR is an imperative language that we're calling LLET star. The user has to explicitly annotate capabilities and fences for array accesses. And our type checker then uses these annotations to extract memory dependencies as explicit data dependencies, and it elaborates the source program into the second IR called LLET. So the reason that we need these memory dependencies represented as the explicit data dependencies is because in the end, the dataflow circuit is asynchronous and does not have any control flow built in. And the operator can only synchronize through data dependencies in our hardware abstraction. We then pass the elaborated LLET program to the core passes of our dataflow compiler, which converts LLET to a simple dataflow calculus that we define called lflow, where we convert basically all the imperative control flow to pure dataflow. And in these core passes, we first compile each function, and they are modularly linked in a separate pass into a single dataflow circuit. And in the final pass, we perform some optimizations and rewriting to make the dataflow circuit smaller and more performant. So in Wavelet, we formally define and verify the two core passes in the Lin theorem prover, proving semantic preservation and a property that we call determinacy, which basically rules out data races in the dataflow circuit. And some of the assumptions of our determinacy theorems are validated by the front-end type checker through SMT solving. So in this talk, I'm just going to give two high-level examples of the two crucial passes in our pipeline, which are the verified core control flow conversion in the middle and the capability type checking in the front end. So let's start with the pass that we call control flow conversion. So this is the dataflow circuit that I've been showing as an example. And this was actually compiled from this simple function on the left, which kind of computes sort of a dot product between two arrays B and C. And it's written in a tail recursive form for a simpler correspondence. So the circuit on the right might seem a bit complicated, but let's see how the different components here correspond. So the function parameters correspond to these carry operators at the top, which takes in initial values for these parameters and also merges any values from tail recursive calls. So you can see there are some back edges from rest of the circuit to these two operators. And the branch condition is computed by this comparison operator. And the result is passed to some of the triangle operators below, which activates the circuit corresponding to the correct branch. Then we have the true branch, which consists of some memory loads and some arithmetic operators. And finally, the false branch just corresponds to this output channel R, but it's also gated by this triangle steer operator, depending on the branch condition. So we define this compilation pass in Ling in a way that's similar to this correspondence, and we prove a forward simulation theorem that the dataflow circuits simulates the behavior of the imperative source program. In other words, if the imperative source program has some trace of memory interactions, then the dataflow circuit can also execute in a way that exhibits that trace. However, forward simulation doesn't rule out additional bad behaviors on the dataflow side. For example, what if the dataflow circuit has a data race and can have a different result if the memory operators are scheduled differently? And the way we prevent that is by proving something called determinacy, which basically means that the dataflow circuit needs to have a deterministic result. To see why that's a problem, let's tweak our example a bit. First, let's remove the return value here and just make it a unit. And we also remove this accumulator argument R here as well, and replace it instead with a memory load and store. So we're basically storing and updating the results in the memory instead. But this circuit is a bit problematic because there is an implicit read after write dependency enforced by the sequential control flow that sort of gets lost in the compiled parallel dataflow circuit. So the load in the next iteration may happen before the store in the previous iteration has finished. And one of the solutions for this issue is to add an extra data dependency between memory operators. For example, here we can introduce an additional backhatch from the store to the load to send a memory synchronization signal. So that load in the next iteration will always wait for the store in the previous iteration to finish. So now the question is, how do we sort of manifest this extra data dependency in the source program as well, so that the programmer can more accurately and soundly control how the synchronization should be done? And our solution is to use a capability type system in which we annotate each function in the source program with the required memory permissions. For example, here f needs to have the capabilities for accessing arrays b, c, and the pointer r. And the reads and writes of these arrays will consume these permissions, which are affine. And when you need to reuse them, you need to add an explicit fence annotation to kind of recycle the used permissions. And these fence annotations will then later manifest as these explicit memory synchronization dependencies through an elaboration pass that I briefly mentioned before. So I talked about two main pieces of our dataflow compiler. Now, how do they fit together to formally guarantee the correctness of dataflow compilation? So with the same example, let's call the input imperative program D, and on the right we have the compiled dataflow graph after control flow conversion. And if we take their semantics, we've mechanized the theorem that the source program is simulated by the compiled dataflow circuit. That is, the dataflow graph has at least one behavior trace that is equivalent to the source program D. For the deterministic part, what we did is that we formalized sort of a dynamic capability checker in the semantics. So guard of D here is the same semantics as D, but with capabilities dynamically checked in the semantics. And the semantics would get stuck if suitable capabilities is not satisfied during execution. So the progress of this guarded semantics is validated by our type checker, meaning that it checks that all operations during execution will always have the suitable capabilities on any inputs, and this is done through SMT solving. And on the dataflow side, we can apply the same capability checker, and we prove that the simulation is congruent with respect to this guarded semantics, so we can directly use the simulation theorem above to prove that the guarded semantics also have a simulation. And then by sort of propagating the progress of the imperative side to the dataflow side, we can prove that the dataflow side is also sort of has this progress property in the guarded semantics, and we prove that this implies that the dataflow circuit is race-free and deadlock-free. So let's zoom out from the details and talk about the evaluation. So in the evaluation, we compared our dataflow circuit wavelet with two existing unverified dataflow compilers. The first one is Wavelet, which is a general purpose CGRA focused on energy efficiency mostly. And also LLVM circuit, which is in general a collection of IRs and compilers based on MLIR for hardware design. But we're comparing with a specific compiler pipeline in it that does dynamically scheduled HLS. For Riptide, we simulate the resulting dataflow circuits and compare the performance and size of the resulting circuits across 10 benchmark programs. And the result is as follows. So for both graphs here, lower is better. So as one bit of a detail, there's an optimization called streamification in Riptide that we do not support yet. So for one category, we disable that for a sort of more apples-to-apples comparison. Overall, we are about 1.7 times slower than Riptide and producing dataflow circuits that are about 2.3 times larger without this streamification optimization. And the main difference here comes from different memory synchronization strategies where we use a more explicit mechanism for synchronizing potentially different conflicting memory operators, which leads to larger circuits and slightly slower speed. But I do want to note that we did actually find some bug in the Riptide compiler on one of the programs that would cause a data race in the dataflow circuit. So this trade-off is meaningful in improving the correctness guarantee. The second comparison is with circuit in dynamically scheduled HLS. So here, for both wavelet and circuit, we're compiling the source programs to dataflow circuits and then lower them to RTL. We're comparing their execution time estimated from RTL simulation as well as the resource usage when targeting an FPGA. So in average, we're about 1.2 times slower than circuit, but we use less resources because of a different choice of control flow operators. Okay. Yes, the last slide. Yeah, thanks. So in conclusion, Wavelet is a dataflow compiler with its core passes formally verified in Ling, and we use the capability types to guarantee the determinacy of the compiled dataflow circuit. And our evaluation shows that our compiler produces circuits that are about 1.4 times slower on average than existing unverified dataflow compilers. And you can find out more about Wavelet from our paper and GitHub repo. Thank you so much.